In this video, I am going to talk about the theory and application of the linear discriminant analysis. The linear discriminant analysis is in short known as LDA. So it's a type of classification algorithm which uses the Bayes theorem to classify data. It's a popular technique when the number of classes to be classified is more than 2. When you have only two classes to be classified, uh, the uh, the most popular technique used is the logistic regression. You can also use the linear discriminant analysis to classify data into two types, but the popularity of LDA is more when the number of classes is more than 2. Now let's compare how theoretically these two algorithms are different. In logistic regression, we compute the probability that a particular observation belongs to a specific class by this. So here is an example. We want to find out what is the probability that uh, a person gender is male, given that his height is 170 centimeter. So what we try to do here is we build a model which takes input as height. We give it takes a value, and based on this value and based on the output from the regression model, it finds out what's the probability. So the probability of somebody being male or female comes from the explanatory variable height. Okay. Or in statistical terms, we try to find out the conditional probability of gender being male for somebody given that height is 70 centimeter. Okay, so that's the conditional probability. Now in the linear discriminant analysis uses a different form of finding out the probability. Okay, so how it finds out? Well, it finds out what is known as a posterior probability. We'll come to that. So before that, it first finds out what is the density of distribution of an explanatory variable, given that a particular given that the class is male or female. Okay. Now the height, the explanatory variable height will have different type of distribution for male and female, right? So what it tries to do is that it finds out the density function for height differently for male and female, and then use this density function in finding out what is known as the posterior probability, and using posterior probability it classify the data into two or more categories. So in this case there are two categories, male and female. Slightly complicated at this stage, but when we take an example it's going to be much easier. So we'll take an example. Before that, a snapshot of how the computation happened. Well, there are two terms involved in this case. One is the prior probability and the other one is the density function. Getting prior probability is very straightforward. You get it from the data itself. Say for example, you have got 10 observations and then 4 are male and 6 are female. So the prior probability is nothing but if you choose randomly from this population, then what is the probability of finding a male? Is nothing but 4 by 10, right? And what is the probability of finding a female if you randomly pick somebody from this population? It's nothing but 1 minus 4 by 10, right? Which is something but 6 by 10. That's nothing but prior probability. which you can compute directly from the data. The next one is the density function. You can compute the density function from the explanatory variable that is available with you. Once the density function and the prior probability we have computed, we can put it in the Bayes theorem, Bayes formula of finding out the posterior probability. Now, what is posterior probability? Well, it's just a fancy term used to find to say that probability of a particular observation falling into a particular class. Okay, so a probability that y belong to the kth class given the explanatory variable taking some value. So now this is the conditional probability of y taking belonging to a class given your explanatory variable takes a value of x, okay, is given by this formula. Okay, now pi k is nothing but the prior probability of the class. Okay, so we have got two here, male and female, right, in this example. And if is the density function that is computed for each of these classes. Okay, so we have got female density function and the male density function. Okay, now once you have these values, put it in the formula, you will get posterior probability. So how will the posterior probability look like? You'll get values like 0.5, 0.6, 0.8. So it could be like probability of y taking male is equal to 0.7. So probability of y taking female is 1 minus 0.7, which is 0.3. So given that the posterior probability is more for male, we consider that observation to be male, right? Okay, so that's the way it finds out. The difference is that the difference between logistic regression and this one is simply in the computation part, but the approach to find out or to classify the data is very similar. Okay, so we'll take a very small example. So we have got 11 observations, male and female. For male we assign it as 1, for female it is 0. Okay, and we have their corresponding height. Okay, so this is the male height and this is the female height. Now we try to find out what is the prior probability. Well, there are 6 males, so prior probability is 0.54. It's nothing but 6 by 11. Okay, and the prior probability for female category is 0.45. You just subtract it from 1 minus prior probability for male, which is 0.54, and gives you 0.45. Okay, so one of the term that is required to find out the posterior probability, we have found it out. Okay, the next one is the density function. Now how do you find out a density function? It's difficult, it's not that easy. Well, in this case you will see height as a continuous variable, so you can plot it out. Now I have plotted the density function is a kernel density function for height. Okay, in two different graphs. One is for male, so this one is male and this one is female, and you can clearly see the distribution of male height and female height is different. Okay, so the maximum you can see the male height lies between 170 to 180, whereas the female height lies most of the female lie between 160 to 165. So there is a significant difference between the average height between the male population and the female population. Also, the distribution is different in terms of parameter. Maybe the type of distribution could be same, right? both of them could be following a normal distribution. Now, how do we ensure that it takes a theoretical distribution or distribution which is well known to us? A number of times the distribution of this continuous variable is considered to be, or uh, is very similar to a normal distribution. I have taken a simulated data, so it comes like that. But if you take a height population, you will find the distribution to be very close to a bell curve. Okay. Now, given that we have this distribution in place, we can always find out the parameters for this distribution, right? So what are the parameters of a normal distribution? The mu and the sigma, the mean and the standard deviation, or the or maybe the variance. Okay, mu and the variance, right? You can find it out once the density of this particular data is known. You can just plug these values in the base formula and find out the posterior probability. Now, once this posterior probability is found out, how do you classify? Well, this is the way we classify. We define what is known as a decision boundary. That means at what probability level we classify data into two categories. Okay, like in the case, it could be posterior probability 0.5. Anything greater than 0.5 is male, and less than equal to 0.5 is female. Okay. It of course depends on the analyst to see which will be the correct decision boundary for this, but there are some optimal algorithm also which finds out what will be the optimal decision boundary, although it can be changed according to the need. That means one can be more conservative. The approach could be more conservative or more lenient. So as you can see on this slide, there is a distribution of two different data, and you can see there is clear difference, and a decision boundary which is the optimal decision boundary is found out where you can actually separate the two data or two classes. So this is the distribution of the posterior probability. Okay. Okay. Now the next thing to do is we'll do a linear discriminant analysis in R. It's not very important to learn the theory before you actually do it in a software. If you are clear with the basics, like how it works and how is it different from other classification algorithms, you can you can still go ahead with implementing this algorithm. Although if you are interested in the theory, you can learn more about it. So I'm going to take a data set. I'm going to take a data set from the library ISLR. Now this is how the data set look like. The name of the data set is market, or it's nothing but the stock market data. Okay, you have got the year, got from 2001 to 2005. I'm showing you only the first 20 observations, so all the data is not on the screen, but you have got data for 5 years. Then the price movement, okay, for lag 1, that means previous day data, and then lag 2, a day before previous day, and then lag 3, 2 days before previous day, and lag 4, and so on. And the volume of trade in some unit, and one more important variable, the direction, whether the stock price has gone up or gone down in the next day. So this is the variable of interest. We want to predict whether stock price is going to go up or go down. Okay. Now okay, so we'll use the linear discriminant analysis to find out the probability that a stock price is going to go up or go down, given the information of lag 1, movement of price, lag 2, and the volume of trade. Okay, so how are we going to do it? Well, we're going to use the function LDA to do that. So the syntax is like that, like this. You store the output in a variable, and then the model is defined like this. The dependent variable is direction, and we are using 3 independent variables in this case. You can of course use any number of independent variables, lag 1, lag 2, and volume, and the data which is being used is market. When you run this code, you will get an output like this. You will get the prior probability of groups, as I have already demonstrated. What is a prior probability is nothing but the percentage of population or percentage of down in the population and percentage of up in the population, which are simple things to count. And then there are group means. You will see the significant difference between the group means with lag 1 and lag 2 and the volume. And with this information, the density function is also computed, and then the base formula is used, but all that is being taken care of by the algorithm, so you don't need to worry about the theory. You'll get the coefficient of linear discriminants. Okay, so the lag 1 coefficient is 0.69 and the lag 2 coefficient is 0.40, and the lag the volume coefficient is 1.2. So that's the output that you will be getting in the LDA, and you can actually use this to predict how the model is doing. Okay, so we'll use the same data set for prediction purpose as well. So how do we do that? Well, we use the function predict, and we have already the estimate. So estimates are all stored in LDA fit in the previous step we have done, and then we use this same data. You can of course use a new data, but given that we do not have a new data in this case, you can always use a train and test data, but I haven't done that because of my laziness. So I'm going to use the same data to do the prediction, and then I store once the prediction is done, I store the classification. It's going to classify the data from market using the fitness statistics, and it's stored in the class variable. So I'm going to take it to another variable so that I can do a tabulation. You can of course use the directly in the tabulation, but yeah, I'm just keeping it in another variable just to make it more simple. And then I have got now the predicted values and the actual values, the actual ups and downs in the data that we have seen. So the actual values are here in the direction, which is the dependent variable, and the predicted values are in LDA class. When you tabulate it, you will get the cross tabulation. Okay, so down, stock price down, predicted, and actual 147 cases, and then the mismatch in this case is 129, where it is actually down but predicted as up. And then there are also mismatches here. So the off diagonal cases in confusion matrix, this is known as confusion matrix, where you tabulate predicted and actual values. So the off diagonal elements are the mismatches and the diagonal elements are the matches, right? So the percentage of accuracy is 147 plus 519 divided by the entire count. Okay, I guess there's some 1202 or something. Okay, so this is the percentage of population correctly classified by the linear discriminant model. So this is how you build an LDA model in R. For all our videos and codes and dataset used in this video and in our other videos, you can visit our website analyticsuniversity.com. Thank you so much, and please don't forget to subscribe to our YouTube channel for more videos.